In this video, we're going to find the electric field due to a ring of charge. I've drawn a ring of radius r sitting in the xy plane, and we want to find the electric field at a point P along the z-axis above the ring. This ring will have a uniform linear charge density lambda. We'll look at a small portion of the charged ring. Notice that the way we've placed our coordinate system, for every small portion of the ring on one side, there is a charge on the opposite side of the ring. This means the x and y components of the electric field will cancel because there is always a charge with the opposite components of electric field. However, they all have a z component that points upward. So this means we just need to find the z component of electric field from a small region and then account for the total charge of the ring. Since we're looking at a single point of the ring at a time, we can approximate the charge's field using the field of a point charge. Each charge will be a distance r away, and we'll use cosine to find the z component for the angle I've drawn. This problem is different from our line of charge from the previous video. Each charge on the line was a different distance away from the point P. Here, each point on the ring is the same distance away and will contribute the same amount to the electric field. We can take our equation for the z component of electric field due to a single point on the ring and write everything in terms of z, the distance from the ring, and r, the radius of the ring. Now, everything in our equation is constant, and the only piece that needs to be summed up is the small charges. Adding up each little point charge along the ring just gives the total charge of the ring Q. And this is the final result for the electric field, a distance z above a ring of charge with radius r. Technically, we integrated the charge, but we didn't actually need to write down an integral and evaluate at limits or anything like that. This is because of symmetry. There are other ways to solve this. We can use an integral and the linear charge density of the loop lambda. Writing our equation for the electric field of a point charge, we can integrate over the charge. But densities allow us to account for the charge by integrating over a coordinate instead. We can write the small charge dq as the charge density times the small length ds. This is the small arc of our ring with the charge dq. We can write the arc length as the radius times the small angle, or r times d phi. Basically, we are finding the electric field of this small piece of the ring, and then we will sweep around the ring, accounting for the full circumference of charge. Again, writing things in terms of z and r, we factor out our constants, leaving only d phi in the integral. Be careful not to confuse the angle theta made with the z-axis and the angle phi of the ring itself. The ring makes a complete circle, so we integrate from 0 to 2 pi. This result looks slightly different, but the linear charge density can be written as the total charge divided by the total length. The length of the ring is just the circumference, or 2 pi r, and so doing this substitution, we regain the same result as before. We can also plot the electric field, but we should have an idea of what we expect it to be. At the center of the ring, there is no z component, and the x and y components still cancel, so the field should be 0. Far away in either direction, we expect the field to get weaker, and the field points away in the positive z direction above the ring, and in the negative z direction below the ring. So if we plot the electric field as a function of z, we see this indeed holds. We see the maximum electric field strength is slightly less than 1 radius from the center. Closer to the center and the field cancels, further away the field drops off as usual. To summarize, there are multiple ways to set up and solve these types of problems, so it is good to practice different ways and understand the motivation behind it. Then choose the approach that makes more sense and feels more natural to you. This problem in particular had symmetries that made it simpler than the line of charge, in that each point on the ring contributed the same amount to the field. We also got results that at first did not appear to be the same, but after some substitutions, we found them to be equivalent. You'll find this to be true in examples you find online or in textbooks. It may look different than what you expect because it was solved in a different way. You shouldn't think your answer or their answer is incorrect, but try to use substitutions to see if they are equivalent and understand how they came to their answer. That's it for this video. I'll see you in the next one.